So in Clark Kimberling's Encyclopedia of Triangle Centers, the two isodynamic points are actually labeled X15 and X16. Let's take a look at X15. So let me fast forward to that by searching for it. And here's X15 in this very long text file, which is the first page of ETC. And here it is. This is the first isodynamic point. Now I have a set of trilinear coordinates and a set of barycentric coordinates. In this video, I'm not going to get too much into what each one of these are, but I'm going to try to implement in GeoGebra this particular expression here, which is more approachable for the barycentrics of X15. I'm going to do two things in this video. First of all, I'm going to show you guys a command that can quickly locate, a GeoGebra command that can quickly locate a triangle center in Kimberling's list, at least the first 3,000 of them in a triangle, and then I'm going to try to implement it using this particular expression for the barycentrics. We'll come back to this. So let's go back to our construction for a triangle ABC, which we used on the previous two videos. And I'm showing here that the two isodynamic points X15 and X16 are indeed intersections of three special circles known as the Apollonius circles. And we constructed those in the previous two videos. I'm going to leave a link right now at the top right hand corner of this video. Okay, now I want to first of all show that we can very quickly access any one of the first 3,000 triangle centers on ETC by simply typing triangle center and then the vertices of the triangle. Triangle center. Let's see, okay, I probably got into some weird thing. Triangle center ABC, and then a number out of Kimberling's list. So here's X15. It's labeled as L. Let's go ahead and label this guy as X_15. And here it is. Now you can see that with one command, I can immediately access a particular point in the plane of a triangle, particular triangle center. And it just so happens that this X15 that I just created, this black dot here, coincides luckily with the geometric construction that we used, namely the intersection of three Apollonius circles for X15. Likewise, I could check if, and this is sometimes useful to see if your construction is correct, if X16 is correct. So let's go ahead and create X16 over here, and I'm going to say triangle center of the same triangle ABC, and now I want the 16th center. And indeed, you can see that X16, this new X16, falls directly on top of the X16 that we computed by intersecting the three Apollonius circles. So that's great. Now what I want to do now is something a little more clumsy, especially with a tool like GeoGebra, which is I want to compute X15 using the barycentrics, B-A-R-Y, barycentrics of X15 as documented on ETC. So here's an expression. So you can see here that following the title X15 first isodynamic point, Professor Kimberling will lay out several equivalent sets of coordinates, or trilinear coordinates and barycentric coordinates. Okay, now let's go ahead and use barycentric coordinates. And I'm going to take this form here because it's the simplest, quickest one to implement on GeoGebra. And let's first of all decrypt or unencrypt what this expression really means. Okay, so you can see here that there's lowercase a, lowercase b, lowercase c. There's a square root of 3. These are the side lengths. This is the side length, little a, opposite to vertex big A, that's little a. Little b and little c are the side lengths opposite to vertices, uppercase B and uppercase C. And S is a special symbol often used on ETC, which is one of the Conway triangle symbols. Okay, this particular one here, capital S. So let's go ahead and switch to Wolfram Math World, Conway triangle notation. And you can see here that there are several symbols, big S, S sub phi, S sub A, and so forth and so on. But we're interested in big S, and that's simply twice the area of the triangle. So what I'm going to try to do now is construct X15 using the barycentrics documented here on ETC. So let's go ahead and place this page perhaps to the right of our screen, like so. Okay, so we can see both of them at the same time. And I'm going to go back to my construction. Okay, and I'm going to try to implement this formula over here. So the first thing I need are the three side lengths, little a, little b, little c. So what I'm going to try to do is, I'm going to try to make them be explicit variables here on GeoGebra. And because I want to avoid collisions with previously assigned variable names, I'm going to call little a, little b, little c, LA, LB, LC. Okay, so let's go ahead and say LA is the distance from between vertex B and C. Okay, so that's giving me that this distance from B to C, which is opposite to A, the side length here is equal to 9.76. Let's do the same for the B side length, which is going to be the distance from C to A, and the C side length, which will be the distance from A to B. You can detect here there's some cyclicality, right? So you're basically replacing B by C, C by A on the first iteration, then you're replacing C for A and A for B on the second iteration. So I have the three side lengths here, and they're numerically shown. I can put in GeoGebra, I believe, more precision. I think if I go to settings here and I say that I want to see, for example, 4 decimal places, now I can see my distances with more precision. Okay, that's all very nice. So the other variable I need is 2 times S, which is 4 times the area of a triangle. But let's just actually compute Conway's S. And I'm going to call this Conway S. Okay, like that. And that's basically the area. It's twice the area of A, B, C. So there it is. The area of this triangle is 79 and something. Of course, I can change the position of these 3 vertices, and I can watch here interactively what's happening to the 3 side lengths and the area. Now let's go ahead and try to build these barycentrics. Let's build. You can see that there is a double colon in the end, implying that I actually need to repeat this expression here thrice or twice, but replacing A for B, B for C, and C for A. So I have to do this cyclically. These 2 colons on ETC mean that this expression is going to be repeated cyclically. Exactly what do I mean by that? Let's go ahead and spend some time with that. So I'm going to do a new, let's go ahead and do this by hand. So if the first expression is that one on ETC, and let's start replacing this by something that we understand. So let's place LA here, or something that GeoGebra rather understands. And this guy here I called Conway S. Okay. Now notice that the area of a triangle is not cyclical, right? It doesn't matter the order of the sides that you pick to calculate the area. It's not order dependent. So I don't need to worry about this variable, this Conway S variable. But let's go ahead and, so we're going to call this is my first barycentric. This is BA. My second barycentric is the same expression, but every time you see an A here, BB. Okay, I want to replace this A by a B. Okay, like so. And every time I see a B, I want to replace it by a C. And if I see a C, I want to replace it by an A. So essentially what I'm doing is A goes to B goes to C, and C goes to A. This is what I mean by cyclical replacement or substitution. Let's do the third variable, BC, C. So I'm doing this third thing. And I can just visually check here if I have the letters in order: ABC, ABC, BCA, and CAB. So it looks like everything's fine, and I have 3 expressions I'm going to need to create a new point. Now let's talk about what barycentric coordinates really are. They're homogeneous coordinates, and in the end, let's say you have a triangle that has 3 vertices A, B, C. If I'm given these 3 numbers, BA, BB, and BC, I can compute a point in the plane of a triangle by simply making a weighted sum of the 3 vertices. So I'm going to do BA times A plus BB times B plus BC times C. So I took my my 3 barycentrics, and I did it this way. I combined them with the vertices. These capital letters here represent points, which are the vertices of the triangle. And now I need to normalize this by the sum of barycentrics. These are homogeneous coordinates, so it doesn't matter what, they're equivalent up to a scale, right? So in order to obtain a new point, which I'm going to call P, if I'm given 3 barycentrics, I obtain this, this point P, okay, on the plane of the triangle by simply executing this formula. Now let's go ahead and see if GeoGebra is friendly. And let's see if I can simply cut and paste something like this into GeoGebra, and if I can actually do that. Okay, looks like GeoGebra took it in. You can see here that it actually accepted this formula. Let's see if the whole thing is there, and it's giving me a number, BA. Let's do the same thing for BB. I'm going to copy it. And let's do the same thing for BC. I'm going to get this formula and copy it here. All right, and now I need this high-level formula here, which is going to give me a proxy for X15. I'm actually implementing this weighted sum of the three vertices of my triangle, A, B, and C, which are the variable names on GeoGebra, so I can keep those there. And let's actually now cross our fingers. I'm going to call this guy here P15, okay, so that I don't clash with anything that might already be there. So let's do that, and let's see if GeoGebra is taking this formula correctly. And it looks like it did the right calculation. It's giving me 9.6681 and minus 0.753. Okay, now let's look at, and this is where we cross our fingers, where P15 is falling on the triangle plane, and it looks like it fell exactly on top of X15, which was computed via the TriangleCenter command in GeoGebra, and it's also falling on top the X15, which is at the three intersections of my three Apollonian circles. So I'm going to leave as an exercise for you guys that you follow these three steps, or actually you do the very last calculation via barycentric. So you have to look X16 up on ETC, and I want you to actually draw a P16 via the barycentrics of X16, which will hopefully fall on X16. So let me know if you're able to do that exercise, and I'll see you on the next video. Thank you.